All right. Thanks everyone for coming in on Friday. I assume you're all looking forward to a free beer, but maybe I'll try to convince you on some other topics which probably everybody has touched upon in their PhD life right now. So the topic is a bit thought-provoking. I've titled it as Programmers or Core Charlatans. But before we start, maybe it's good to know how many people here use Copilot or Cursor or any of these fancy AI code assistants. If you can raise your hands, like, wow, everyone. Okay, fantastic. So maybe I will convince you that you shouldn't pay your $20 to them every month and save it on a pizza or something. Okay, so the way we are going to start is let's look at the scenario. So code is a structured language environment. It is quite volatile and dynamic, right? Every library undergoes a lot of changes as it becomes popular because more and more users use it. There are new features added, some old features are depreciated. So it undergoes a lot of changes, and because of this change, it becomes imperative that we have language models that account for these changes and are aware of what changes undergo in these libraries, right? So imagine you're a software developer, you create a library, and then you went on a holiday, and now you come back and you see the library has undergone 3 different version changes, and you don't know what has happened. You have to go through the commit history, understand what the version change meant, and then accordingly adjust your workflow, right? And the same exact scenario is for a language model that generates code bases, right? Because they're usually not made aware of these version changes. And I'm just a PhD student earning maybe a minute amount of what these people earn. So you don't have to be convinced by me. You can hear them out. They say that, okay, like all of our code bases is now partially being written by AI, which is great. But is it really the case? Like, can they actually write production grade software? Maybe not. So let's look at a couple of examples where they fail, right? So if you give, in this case, GPT-4 or Mini, a problem statement to write some specific functional level code using 2 popular libraries, in this case, pandas and Seaborn and GeoPandas, with a very specific version, right? Like GeoPandas 0.9 or using a specific version of Seaborn, then they both fail because one of them gives a type error saying that it got an unexpected keyword because that specific version of GeoPandas for that API call had nothing in its argument called predicate. And the same goes for Seaborn. It gets an assertion error saying that BW parameter should not be used and should instead use 2 other arguments to that API call. So basically, because the model doesn't know what changed from one version to another version, it's just using the mode over all the versions. So the maximal samples it has seen for a specific version for library, it is using that, but that doesn't necessarily mean that it adheres to the true version that you're requiring it to produce the code for, right? Okay, so here is what we do. So we first introduce a benchmark called GitChameleon. This is a Python-only benchmark consisting of 328 samples from your favorite libraries like Torch, GeoPanda, SciPy, NumPy, but basically consisting of version-sensitive samples. So like asking it to write a specific API call, but in a very specific version. And we validate this by tests. For each sample, we have hidden and visible unit tests, which has 96.5% coverage. But let me first tell you about the collection protocol, and then I'll answer the question if LLMs can do this task or not. So first, we identify the change from one version to another, and it has to be a surface level change. Then we manually write assertion-based visible tests, and then we generate hidden tests using an agentic framework. But what constitutes a change? So in this case, because we are only interested in high-level changes, a change can be something like the argument or attribute of an API call changing. So assume there was an argument called predicate, which didn't exist before, but now exists. So, and you need to use that argument when calling that API, then that would be considered a change. Or if the API call changed, so earlier maybe you were using Adam as torch.nn.adam, and now it requires to be called as torch.nn.optim.adam. That is considered a breaking change. the semantics change. The semantics basically mean the behavior of the function changed. Let's say the function earlier was giving just a single vector as return, but now it is giving you a tuple of two vectors. So you need to account for that when invoking that function. And new feature is pretty obvious. So like take example, shampoo as an optimizer. It didn't exist before Torch 1.7, was introduced in Torch 1.8. If you are using 1.8, then you call directly shampoo from the nn.optim class. But if you are using 1.7, then you have to write it sub-inheriting the optimizer class, right? What doesn't count as a change is anything that includes nightly version, yank releases, or low-level changes, like the C++ backend of Torch changing to introduce better numerical stability to a function doesn't really changes the code that you write to call that API. It just changes the underlying precision ability of that function, so we don't account for that. All right, given that we know, so this is how the structure looks like. For every problem, you have a problem statement written in natural language. You have the starter code, which is essentially writing all the imports and the function that you want the model to fill in, and some inline documentation. We have metadata for each problem. Then, of course, we have expected solution, the manual assertion-based visible test, and auto-generated hidden test. We only pass the problem statement and the starter code to the model, right? Okay, so let's look at the fun part, which is, can language models actually write version-specific code? And the answer is no, TLDR. Let's look at enterprise models. So all the latest models that you can imagine, GPT 4.1, Claude 3.7 Sonnet, Grok 3, the best we can achieve using greedy sampling is 50%. So we have three metrics here: hidden, visible, and API hit rate. The ranking is done by hidden tests because they have higher coverage than visible tests. API hit rate is just a metric to see if the model can invoke the correct API, regardless of whether the arguments within the API are incorrect. So as you can see, in our case, the best model is Gemini 2.5 Pro. So just being able to do nearly half of the total sample set correctly. And we can get as bad performance as like Command R plus, which can only solve 1/3 of the problem. And these are all industrial grade performing models, right? By the way, the prompts are all black box optimized. So this is the best possible result you can get in greedy sampling. The same goes for zero-shot chain of thought. And in this case as well, the best performing model is hovering around that 50% success rate through hidden tests, and that is by GPT-4o. And so you barely can ever get higher than half of the total data set being solved. And not just enterprise-grade models, open source models are equally as bad, if not worse. In our case, the best open source model that we tested was Qwen 2.5 VL that gets around 48% top performance. And in this case, we always considered structured response format from the model. So that is why we didn't use all the open source models, because all open source models don't support structured querying. So, but regardless, what I'm trying to convince you is that these models are pretty bad. But these are all through API calls, and I believe nobody here uses API call in their code writing procedure. So let's try something more powerful. Let's try RAG. In this case, the documents are the API documentation of all the problem statements that we have in our data set. So basically, if one of our problem is about the shampoo optimizer from Torch, we literally go to Torch, search shampoo, the documentation, embed it using the text embedding large model from OpenAI, and we create a vector database, and then we just retrieve the top 3 documents given the query. And you can see even with RAG, the best we are able to get is 60%. Of course, it has more context now, but it still cannot solve the data set, even if you're providing the ground truth documentation to the model. But you still wouldn't use RAG. But before we go to the next one, I want to show one interesting insight is that the larger the model is, the better it benefits from RAG. So what you're seeing over here is the improvement over the top 10 libraries in terms of sample count we have in our data set. So you can see for GPT 4.1, it improves more libraries than it hurts in terms of performance. But as the model becomes smaller with RAG, the performance actually decreases for more of the libraries as compared to for which it increases while providing this context. So It's just a deviation from the original findings, but nonetheless very interesting in my opinion. Then the next one is agentic framework. And in here, we use a single base model, Claude 3.5 Sonnet, and we have different tools like DuckDuckGo search, Perplexity search, or Gemini grounding. And we have the same tools, but with star, which represents sandbox, which means it can execute the code that it is generating and use it as feedback. So it will just run Python that code .py. And if it doesn't compile, then it will use the error as a feedback to improve it. So you can see even with this, the best we can do is like 55% with Claude 3.5 Sonnet through DuckDuckGo search engine querying. But you still wouldn't use this. You would use this. So code assistants. So these are all Visual Studio or command line code assistants that you can install right now. So here, Claude Code and Goose are command line code assistant frameworks that you can directly use from the command line. And Klein, RuCode, and KiloCode are Visual Studio extension-based code assistants. And you can see that even with code assistant-based app completion that you use in Visual Studio Code, it's still really, really bad. The best that you can get is through Goose at 56% pass at one. So let's look at some more analysis in terms of what kind of changes do models are really bad at. So we found that feature addition, which makes sense, like one version of the library introduced a new feature, like shampoo was introduced in Torch 1.8. If the model hasn't seen enough instances of this new feature in this target version, it just can't write it correctly. So we see that out of all the categories of problems we have, feature addition is one of the worst performing across all the models in both hidden and visible tests. We also look at versions across the years when they were released. So from 2021 to 23, we have 2024 as well. The reason we keep it within these years is because we ensure that all the versions are within the training distribution of the model. So they have all been exposed to these versions when they were released. And you can see that the most stable is 2021. That is because Stack V2 or V1 primarily on which these models are trained on has a lot of code from stable versions that come from 2021. Can you bootstrap this benchmark by solving other benchmarks in code generation? The answer is no. You could, theoretically speaking, have good performance on SwiBench, and there is some moderate correlation with SwiBench to our benchmark. So it will give you somewhat of an indicator that you could solve it. But if you're relying on other benchmarks like LiveCodeBench, then there is hardly any correlation between solving LiveCodeBench to solving our benchmark. So yes, like what I'm trying to convince you is please use this benchmark to evaluate whether a language model can truly do version sensitive coding. And last but not the least is, can you bootstrap this benchmark by ensembling different models? So I showed you that models can best do 50%. So if one model did the first 50% right, the second model did the last 50% right, then you can theoretically solve it by ensembling. But that is also not possible because most models in all the settings agree on which samples they can solve and which samples they cannot solve. So technically, you cannot even ensemble this. And even if you tried, at the cost that you will incur, you'll maximally be able to solve 60% of the data set. So yeah, to summarize, what I'm presenting over here is that version sensitivity is sort of the desired nature in software benchmarking. If you're not coming from a software engineering perspective, one of the major problems in software engineering is code migration. So you want to migrate from one version to another version. And currently, what I've tried to show you is that language models fail remarkably on this task. Because they are not version sensitive, they're not exposed to how to write version specific code. And what we have tried in our efforts so far is to create a benchmark that can allow you to evaluate these capabilities of these models in a more principled manner. So that's it. If you have any questions, feel free to ask. Thank you.